Welcome back everyone. In this lecture we will continue with the applications of group action. So first we will see the application when we restrict to this conjugacy action. So the group G acts on itself via conjugation. So let's recall what it is. So let G be a group. So then G acts on itself via this conjugacy action. So what it is, so which we denoted by C. So it's a map from G to SG. So given by G goes to this small g, CG. So which is a map from G to G, which sends X to GX G inverse. Okay. So this is the map we called the action of G on G via conjugation. So this is very interesting map. So let's try to understand all the terminologies that we introduce for the group action for this particular example. Okay. So first of all, what is the center as well as the conjugate the centralizer of some element. Okay, let's recall. The center of G is defined to be those G in G such that commutes with all elements of X in G. So that is called the center. Okay, this is called center of G. So now given X in G, so the centralizer of this X is defined to be those G in G such that Gx equal to Xg. Okay. And note that the center is nothing but intersection of all the centralizers of X and then X runs over G. So this is immediate. Okay. So now we want to understand this action. Okay. For that purpose, recall that the set is capital G. So let's start using this set notation, then it's clear what we mean. Then we are also interested in this fixed point subsets. Okay. So recall what it is. This is those elements of capital X that are fixed by all elements of G. Okay. That means whenever you act this capital G on this X, then that should fix this X. So that means G, okay, let me use this CG so that let's not confuse. So this CG of X is nothing but G dot X. Okay. So those X in X such that CG of X should be X for all G in G. So that is your X power G. So if you rewrite this, you can see that X power G is nothing but those X in capital X such that what is CG of X? CG of X is the conjugate of X by G, that is G X G inverse, which is equal to X for all G in G. So what it is? It is exactly those elements in capital X such that commute with all elements of capital G. So which is nothing but the center of G. Okay. Even though this is happening on the set side, since G is acting on G, so this interesting fixed point subset becomes actually interesting subgroup, which is the center. Okay. So now what is the orbit of some element X? So look at the orbit. Orbit is going to be CG of X, where G comes from capital G. So by definition, the orbit CG of X is Gx G inverse and G is coming from G. So this is nothing but the conjugacy class of X. So this is called conjugacy class of X in capital G. So the orbits are also very special. So they are all conjugacy classes and the fixed point subset is nothing but the center. So now recall what is the stabilizer. The stabilizer is Gx. Okay. So for x in capital X, Gx is nothing but Cg of x. Okay. So sorry, stabilizer is a subset of G. This is those G in G such that Cg of x should be equal to x. So this is actually a subgroup of G that we know. So if we unravel the definition, we can see that this is those elements of G such that Gx G inverse equal to x. So which is nothing but the centralizer of x in G, because Gx G inverse equal to x means x and G commutes. Okay. So this equation is same as Gx equal to xg. So in this particular case, the conjugation action, so we have the orbit is nothing but the conjugacy class Gx G inverse, where G in G, and the stabilizer is nothing but the centralizer of x, and this fixed point subgroup, sorry, fixed point subset is nothing but the center, and similarly the kernel of C, that is also center. So all these things are there, we have worked. So now if we go back to this orbit decomposition theorem, and then if we rewrite that equation in this example, let us see what we are getting. So recall what is this orbit decomposition theorem, that tells the cardinality of x equal to cardinality of x power g plus summation the number of elements in the orbit where x runs over some indexing set lambda 1. So what is lambda 1? Lambda 1, those elements in the indexing set such that the number of elements in the orbit should be greater than 1. Okay. So if you look at this orbit, so this orbit is trivial when, so this orbit has at least, okay, you can see that it has x. So x is inside orbit of x. So the orbit is singleton x if and only if Gx G inverse should be equal to x for all G in G. Okay. So that means the orbit is singleton x if and only if x should be inside the center. Okay. So that is what it says. So that means this x power g that we collected, so that will corresponds to the center, and these elements will corresponds to elements that are not in the center. Okay. So if we rewrite that orbit decomposition, in this case the cardinality of x equal to cardinality of g, and the cardinality of x power g is nothing but the cardinality of the center plus summation, we have this number of elements in this orbit, but using orbit stabilizer theorem, the cardinality of orbit x is nothing but the index of the Gx inside G. So now Gx is nothing but the centralizer of x in G. So in particularly in this case, the number of elements in the orbit is nothing but index of this Gx inside G. So which is cardinality of G divided by cardinality of Cg of x, because Cg of x is Gx here. So if we replace that here, we get cardinality of G equal to cardinality of the center of G plus the cardinality of G divided by cardinality of Cg of x, okay, where x comes from some indexing set lambda 1. So lambda 1 is the indexing set. So this is those x in capital lambda such that the cardinality of Cg of x should be less than cardinality of G. Okay. So this is very, very important. So this indexing set is chosen to be some particular indexing set from capital lambda. Capital lambda identified with this x modulo G. So which is a set of all orbits. Okay. So inside this we are choosing this lambda 1 such that the orbits that are having more than one elements that are indexed by this lambda 1. Okay, this is indexing set of those orbits that are having more than one element. Okay. So, in this case if you translate, that corresponds to those orbits, that means those conjugacy classes that are having more than one element. So, in terms of the centralizer should be proper inside G. Okay. So, this is called actually class equation. So, it is a very important equation that actually kind of encodes lots of information about the finite group. Okay. And of course, we have derived all this for the finite group. So, let us write it here. So, to begin with, we assume the group is finite. So, all this counting business makes sense. Okay. So, let us look at some immediate application of this class equation. Okay. So, let us start with group of order p power n. Okay. This is first immediate corollary. Suppose G has order p power n. So, group that has order some power of prime, those are all called p groups. Okay. If the cardinality of the group is p power n, then we can immediately conclude that the center of that group must be non-trivial. So, if cardinality of G is p power n, then the center must be non-trivial. Not only that, one can prove that it will have at least p number of elements. Okay. And that is immediate, because once center is non-trivial, the center cardinality of the center must divide the cardinality of G. So, it must be some p power. Okay. So, that is why we should have at least p number of elements. Okay. Let us prove this. So, let us recall the class equation. So, recall the class equation. The class equation says the cardinality of G is nothing but the cardinality of the center plus summation the cardinality of G divided by cardinality of Cg of x, where x comes from very specific indexing set. Okay. So, this is our class equation. So, now you can see that if x is in lambda 1, so then the cardinality of Cg of x is strictly less than cardinality of G. So, that means the cardinality of G divided by the cardinality of Cg of x is actually a proper divisor of cardinality of G. So, that means it cannot be 1. Okay. It is more than 1, and it must be a proper divisor. So, that means what? That means the cardinality of G divided by cardinality of Cg of x must be some prime power, okay, for r greater than or equal to 1. So, whatever it is, that simply tells for x in lambda 1. So, whatever elements that are there in this sum, they are all divided by p, that is all it says. Okay. So, if you go modulo p, then it is immediate that, so p divides this cardinality of G divided by cardinality of Cg of x for x in lambda 1. So, that implies p divides cardinality of G divided by cardinality of the center, but cardinality of G is nothing but p power n, that is given. So, that would imply that p divides the cardinality of G. Okay. So, that means the cardinality of the center is congruent to 0 modulo p. So, this proves that the center must have at least p number of elements. Okay. So, p divides the cardinality of the center. So, that implies the cardinality of the center is at least p. Okay. So, this proves immediately this particular result. So, in particularly we can have the following corollary. Okay. So, if you have the order is exactly p square, so then we can immediately conclude that G is abelian. Okay. So, how one can conclude this? So, note that from the previous corollary the center must be non-trivial. So, that implies the center either has elements p or p square. If it is p square, then we are done already, because if the center has p square number of element, then G must be abelian, because center of G equal to G. So, what if it has exactly p number of elements? Okay. So, in either case you can see that G modulo the center of G. Okay. So, this has either one element or p number of elements, but any group of order p is actually cyclic. So, one can conclude from this G modulo center of G is cyclic. I already gave one exercise. Suppose G modulo center of G is cyclic, then immediately one can prove that G is abelian. Okay. So, you can use that exercise to immediately conclude that. So, once you know some information about G modulo the center, in particularly if you know it is cyclic, then we can immediately conclude G is abelian. So, that way we can conclude that when G has order p square, then G must be abelian. So, you take it as exercise, just use some counting argument and then reprove the same statement. Use only counting arguments and prove that cardinality of the center cannot be p. Okay. So, then that would imply immediately the cardinality of G must be p square. So, that would imply that G is abelian. Okay. So, this is something you can do just by doing the counting arguments. Okay. Let us see some more applications of the same result. So, in case if we know actually some information about G, okay, let us say, okay, so this is some immediate observation from the orbit decomposition. So, and the previous arguments, suppose G has order some p power n, okay, and G acts on, let us say, capital X. So, G acts on capital X. So, then what we can conclude from the orbit decomposition, the cardinality of X is nothing but cardinality of x power G plus summation cardinality of G divided by cardinality of G x, where x runs over some index in set lambda 1. So, this is what orbit decomposition says. So, now we can have a closer look at this ratio. Okay. From that, what one can immediately conclude that the cardinality of x must be congruent to cardinality of x power G modulo prime p. Okay. So, this is immediate. So, how one proves this? So, here is the proof. So, let us look at this ratio, cardinality of G divided by cardinality of G x. So, by definition of this indexing set lambda 1, we know that this has to be greater than 1. The cardinality of G divided by cardinality of G x must be greater than 1. Note that this is index. Okay. The cardinality of G divided by cardinality of G x is nothing but index of G x inside G using the Lagrange's theorem. So, that means this number must divide cardinality of G. So, the cardinality of G divided by cardinality of G x must divide the cardinality of G, which is p power n, and this is greater than 1 and divides p power n. So, that forces that the cardinality of G divided by cardinality of G x is congruent to 0 modulo p. So, this is the exact same reasoning that we gave for proving that the center of the p group is non-trivial. So, here we are doing for general set capital X. Okay. So, now since this is actually concurrent to 0 modulo p, so which is some element in this sum, okay, and each element has this property. So, that means if you look at this entire sum, this must be congruent to 0 modulo p. Okay. So, from this you can immediately conclude that summation cardinality of g divided by cardinality of gx, and this is true for all x in capital lambda 1. Using that you can see that the summation cardinality g divided by cardinality of gx, where x runs over this indexing set lambda 1, is going to be 0 modulo p. Okay. So, from this and this orbit decomposition, you can see that the cardinality of x is clearly cardinality of congruent to cardinality of x power g modulo p. Okay. So, this is somewhat immediate for p groups. So, in particularly whenever you know some information about this cardinality of x power g. So, for example, if it is congruent to 0 modulo p, then you can immediately conclude that, so p must divide cardinality of x. Okay. It is a very important corollary. So, let us look at one immediate application of this. Okay. So, we can prove, for example, Cauchy's theorem immediately from this observation. So, let us see what is the statement of Cauchy's theorem. So, which is a very important result in finite group theory. So, Cauchy's theorem state the following. So, again all of this for finite group theory. Let G be a finite group. Okay. If P divides the order of G, then there exists an element of G of order P. Okay. So, this is a very interesting theorem. Okay. There are many proofs that are available for this theorem. One can use, for example, induction to prove this. Okay. So, I will outline the induction, but I want to give direct proof using group action. Okay. So, both proofs actually uses somewhat in group actions, but let us see the first proof. Okay. So, the first proof. So, this is due to James McKay. So, this he proved this in 1959. This appeared in American Mathematical Monthly. Okay. So, that is the proof I want to give, James McKay. So, this is in AMM, American Mathematical Monthly, in 1959. So, this proof is very cute proof. Okay. So, we construct actually appropriate set capital X and appropriate group, let us call it H. That H will act on this capital X, and immediately using this action we conclude that there are elements of order P inside G. Okay. So, unless you are experienced, it is actually difficult to write down this set. Okay. But it is kind of magical. So, construct this capital X as follows. You look at all possible P tuples, okay, G1 etc. Gp coming from G cross etc. cross G. So, this is P number of times, okay, such that because we are looking for elements of order P inside G. So, you collect all P tuples of elements such that the product is exactly equal to identity. So, this is your set. So, note that identity etc. identity, this element, okay, is inside capital X. So, in particularly capital X is non-empty. Okay. So, because the product of identity is just identity, okay, even if you do not know there is element of order P, still you can conclude that X is non-empty. So, what is your group H? H you take it to be this cyclic group generated by the cycle 1 to P inside SP. The SP is the symmetric group on P, let us. Okay, this is the symmetric group on P, let us. Okay. and then you take this cycle 1 to P and then take subgroup generated by this, that is inside SP. So, SP naturally act on this G cross G P times. Okay. So, there is this natural action of SP acts on this G power P, which is G cross etc. cross G. How it acts? It just permutes by permuting the coordinates. By permuting the coordinates. So, in some sense this is what motivates us to define this capital X. The capital X is motivated from this action of SP on GP. Okay. So, now you can use this action of SP on GP to define the action of H on X. Okay. So, define the action of H on this capital X as follows. Again you just permute the coordinates. Okay. You take sigma dot this G1 etc. GP is just given by G sigma 1 etc. G sigma P. So, this is the action that we are talking about. So, why this action well defined? Because the product of these elements G1 etc. GP must be identity in that particular order, because G is not given to be abelian or anything. G is the general group. So, in that group you are talking about specific product in some specific order. So, that product should be identity. So, we have to verify if you use this sigma coming from capital H. So, then this should give you actually the product which is identity. Okay, that can be verified as follows. So, you suppose G1 etc. GP is identity. So, then you can see that G2 etc. GP G1 is also identity by post multiplying G1 inverse and pre multiplying by G1. Similarly, you can permute again G3 G4 etc. GP and G1 G2, that is also identity. So, you can go as follows as this, and this is just a cyclic rotation. Okay. But look at our group, that group is also cyclic rotation group only. Okay. 1 to P which just rotates, which has P number of elements. Then you can see that, so by using this elements of H. Okay. So, by starting with this G1 etc. GP, you end up at somewhere here. Okay. But then again you will be getting the product to be identity only. So, there are this P number of things equations that comes from GP, G1 etc. GP minus 1 equal to identity. So, these are all P number of equations here equal to P, and that is all obtained from by applying various elements of this H on this equation. So, that is what happening here. So, that means this element is also in capital X. Okay. This justifies that H acts on capital X. Okay. Action is group homomorphism bundle can be easily checked, because this action indeed coming from this particular thing. I will leave it to you to check. So, now what is the fixed point? Okay. If you compute x power H, what it is? It is exactly, you can see that those tuples G1 etc. GP such that these are all fixed by H. Okay. Let us call it G bar. So, sigma G bar should be G bar for all sigma in H, but sigma just permutes. Okay, and it cyclically permutes. So, that means this x power H is nothing but exactly GGG, okay, where the product of this G power P should be identity. So, this is coming from H, okay, where it is fixed. So, this is, so that means the number of elements of order P has 1-to-1 correspondence with this x power H minus this identity element, the tuple identity. Okay. So, that tells you that it is enough to verify this x power H has cardinality more than 1. Okay. But go back to our corollary. So, the result that we proved, for if the group is P group, then the cardinality of H is congruent to cardinality of x power H. Okay, the group is H modulo P, that is what we have actually observed. For any P group this is the case. So, to prove that the cardinality of this x power h is actually congruent to 0 modulo p, it is enough to look at the cardinality of x. But what is the cardinality of x in this case? Cardinality of x is easily computed because, so this is p tuples of elements of G such that the product is given to be identity. But this product can be rewritten as follows. Okay, this product actually can be rewritten as G1 inverse equal to G2 etc. Gp. That means, so if you know first p minus 1 coordinates, or if you know last p minus 1 coordinates 2 to p, then the first coordinate can be recovered. That means this can be naturally identified with that g power p minus 1. Okay. So, this is something I will leave it to you to verify. So, verify that the following map gives you bijective correspondence from g power p minus 1 to capital X. What is the map? You take G2 etc. Gp tuple and then send it to G2 etc. Gp inverse comma G2 comma etc. Gp. Okay. So, now note that the product, if you call this is G1, so then G1 times G2 times etc. Gp is going to be exactly identity. Okay. So, that means this is a map from g power p minus 1 to x, and I urge you to verify this is indeed bijective correspondence. So, this is actually bijective correspondence. So, that means the cardinality of x is exactly cardinality of g power p minus 1. Okay. But note that p divides the cardinality of g. So, that implies p divides cardinality of x, because this is exactly cardinality of g power p minus 1. So, that means p divides the left hand side. So, that implies p divides the cardinality of x power h, but x power h has at least p number of elements. If you just take away that identity p tuple identity, okay, E, this is one element. If you remove this, still we have so many elements in this x power h, but any non-trivial element is going to give you order p element in G. Okay. That proves actually G has elements of order p, and this proof indeed tells you that immediate corollary. So, this x power h is actually counting the number of elements of G of order p. Okay, let us say minus 1, or maybe like this is minus 1. So, this is also counts you that number of G in G such that G power p equal to identity, and we have proved this is exactly congruent to 0 modulo p. Okay, because identity is always there in this set, identity power p is going to be identity, but if you think about it, it is exactly number of elements of G order p minus 1, which is exactly congruent to 0 modulo p. So, this you get it as corollary. So, we will see later that how one can generalize this corollary. Okay. So, this Cauchy's theorem also can be generalized again further. So, that is called Sylow's theorem. So, we will prove Sylow's theorem as a corollary of group action again. Okay. So, I will give another proof of Cauchy's theorem in the next class. Okay. I will stop here. Thank you.